So we should imagine you already know a little bit about the Union Chain Bridge project already, seeing as you're here. In short, a 200-year-old suspension bridge linking Scotland and England, crossing the River Tweed, is currently being conserved. Our talk tonight homes in on the Tweed aspect of this. The person who thought of this deserves a medal for creative use of language, in my opinion, but how about this for an acronym? Tetrapod World, Early Evolution and Diversification, which both neatly sums up what Dr. Nick Fraser is going to discuss tonight and spells out the word Tweed. Although I think some significance finds were from the banks of the Whiteadder, though, but it's a tributary of the Tweed. Dr. Fraser is head of the Department of Natural Sciences at National Museums Scotland. He's specialising in vertebrate paleontology. He works in an interdisciplinary way, combining aspects of zoology, geology, and I should imagine any other ology that's relevant to his area of study. His work is of international significance, and he's worked in, amongst other places, the universities of Aberdeen, Cambridge and Edinburgh in the UK, as well as museums in Virginia, Chicago in the USA, and Beijing in China. We thought that having a bridge that was 200 years old was fairly historic, but thinking about what happened 360 million years ago, well, that's quite something else. How appropriate, given that we're a cross-border project, that tonight's talk's title is loosely built around a quote from a border Reaver family, the Armstrongs. So please welcome Dr. Nick Fraser to tell us about one small step for amphibians, but a giant leap for life on Earth.
Thank you, Carol. Can everyone hear? I hope that's okay. Let me see if I can share my screen first of all. Is that working? Perfect. So today I want to share with you something about a really significant period in the history of life on Earth, where fossils from the border regions have made an enormous difference to our understanding of the world. But in order to do that, I would like to set the scene and start by placing the time and the events into a more general picture of paleontology. Where do all the world's most significant fossils come from? Exotic lands, right? Such as the Gobi Desert, or this area around Yixian in northeastern China. And this quarry was the first to yield the famed feathered dinosaurs from the early Cretaceous period. Here's another fossil hunter's paradise, the Bighorn Basin in Wyoming. Fossils present present a really remarkable glimpse of life in the past. But because fossilization processes require very special circumstances, much of past life is not represented in the fossil record. Animals living on land are especially rare. I'm sure many of you will have heard the recent suggestion that there may have been as many as 2.5 billion T-Rexes total that lived over their time on Earth in the past. Yet, we probably have less than 20 decent partial skeletons of T-Rex ever collected. So that gives you some idea of the odds against fossilization and discovery. Nevertheless, there are plenty of remarkable sites around the world, such as the Badlands of Western North America. Great rock exposures like this where abundant fossils are eroding out. In this case, spectacularly rich bone beds with bones extending as a mass graveyard for many meters in one area. And of course, Scotland and northeast England do not really match up to that environment. Cold, wet, and no extensive rock exposure. So the likelihood of a discovery of global significance in this area might seem totally stacked against us in this part of the world, right? Now, I want to pause a little bit more and highlight some key periods in Earth's history that mark major changes that shape life on Earth as we currently know it. Firstly, the last 2.5 million years, the Pleistocene, and in particular, the last Ice Age. Although it only ended 10,000 years ago, which is a blink in the eye in geological time, it witnessed some iconic extinctions. There's still an ongoing debate as to whether humans were involved in the extinction of some of these large terrestrial mammals, such as mammoth and mastodon. Many even use it as a warning for what is currently happening to nature all around us. Now, in all of the examples I'm about to show, note the configuration of the continents around the world as they change through time. So for the Pleistocene, the world's main continents are essentially very similar as they are to the ones they are in today. Going back a little bit further, 65 million years ago, then there is the end Cretaceous event that every child knows witnessed the sudden demise of the dinosaurs. Montana, Wyoming, Alberta, the Yucatan Peninsula, the Dakotas are just some of the places providing us with information about this remarkable extinction event, and with the impact of an extraterrestrial bolide having something to do with that extinction. But of course, it's not all about a trail of death and destruction. There are some key periods that witness key innovations and origins of major groups. And these are just as important in the history of the life on Earth. And perhaps one of the most critical for us is the end of the Triassic, around 220 million years to 200 million years ago. This period not only saw the first dinosaurs, but many of the major groups of modern animals. For instance, mammals, frogs, turtles, crocodiles, true flies, thrips, water bugs, and so on. Note now the very different arrangement of continents, with the world essentially one supercontinent called Pangaea. Right, going back a little bit further, the Permian world, and you've still got this sort of mass of Pangaea forming the central part of the Earth. 250 million years ago, renowned for the great dying at the end of the period, the greatest mass extinction of all time, with estimates ranging from 70% to even 90% of all biodiversity wiped out. That really is a phenomenal event. And somewhat further back in time, from 420 million years to 360 or so million years ago, the Devonian period was also marked by various extinctions through time, but also many firsts. And in particular, it is known for the origin of complex terrestrial ecosystems, as exemplified by the Rhynie Chert in Aberdeenshire, shown here. Now, at this time, what is Scotland today was positioned just south of the equator. Finally, the beginning of the Cambrian, around 540 million years ago. It saw the explosion of life with complex multicellular organisms, some with a certain resemblance to later life, such as the trilobites, but many really anomalous and bizarre organisms, such as hallucigenia and Anomalocaris. Now, that has been a bit of a whistle-stop tour of my view of some of the key events in Earth's history. So now I want to go back to the Devonian, 420 to 360 million years ago. As I said, it too has an interesting extinction event, but for today, I want to concentrate on the early tetrapods, animals with 4 limbs. Now, you might instantly assume that the possession of limbs might indicate a land-living animal, but that is not necessarily so. Meet the fish fingers. So this is Greenland, where the description of these 2 animals, Ichthyostega and Acanthostega, represented groundbreaking work, first by Erik Jarvik, and then later by my friend and colleague, Jenny Clack. For a long time, both of these animals were seen as a kind of missing link in the transition of vertebrates from water to land, and the first vertebrates to have actually moved around on land, supposedly. Fish-like tails and feet with more than 5 digits. That's very interesting animals. Next, meet Tiktaalik, discovered by Neil Shubin, shown here, and his team of Farish Jenkins and Ted Deschler. This particular animal comes from Arctic Canada, Ellesmere Island, in fact. Even more fishy looking than Acanthostega and Ichthyostega, and it doesn't look capable of walking on land. So now beginning to see that there was perhaps a great deal more to the story of the colonization of land. We do know that by 345 million years ago, we had definitive terrestrial tetrapods like this one. This one's called Balanerpaton. But this is still actually a major transition from the fish-fingered type forms to this guy Balanerpaton. And somewhere in here, there's a step in vertebrate history without which we would not be here today. So this step involves going from taking oxygen from water through gills to breathing on land and developing major support structures and sensory systems for sound and vision in air rather than water. This is a massive change, and it must have been developed in stages. So what evidence do we have for the steps involved? Well, it turns out that for a long time, we had virtually nothing. Between the end Devonian, 360 or so million years ago, and a substantial portion of the early Carboniferous, we have very little record of terrestrial vertebrates. So that is for a period in the region of 15 million years or so. And that's what is outlined on the left here in green in this diagram. This ultimately became known as Romer's Gap. Then again, about 345 million years ago, we have moved away from the fish fingers to animals clearly able to locomote on land. This evolutionary step was something that intrigued the great US paleontologist Alfred Sherwood Romer. In between searching for early dinosaurs in Argentina and between writing some of the definitive texts on vertebrate paleontology, Al Romer spent a lot of time searching in the Carboniferous of Eastern North America for traces of terrestrial vertebrates. And as you see on the right, this is him on the left of that sepia tint there. He also found his way over to Scotland to see if he could find any clues. And this is one of the quarries in Fife. If the great man could not find any traces, perhaps this was actually a time of a real dearth of life on land. And theories about lowered atmospheric oxygen levels were even invoked by some researchers. Now, it so happens in southern Scotland and northeast England, there are well-known outcrops of rock, marked here on this map in blue, and these represent the period of Romer's Gap. There were occasional finds, but mostly rather scrappy, although this particular find on the left, on the bottom, sorry, by Peder Aspen near Dumbarton was an exception. And it was named Pederpes, Peter's Foot, by Jenny Clack in the early 2000s. But for a long time, this was the only tetrapod fossil known. Enter Stan Wood into the fray. He actually had no time for theories about reduced levels of oxygen, and he was convinced it was just a question of employing the right search techniques in the right places. And after all, Stan was notorious for his fossil sleuthing skills and had a track record of turning up critical fossils where others had failed. One example of his discoveries seen here is West Lothiana from the Carboniferous of East Kirkton, at the time considered to be the oldest known reptile. So once again, here's the map showing the prime targets for Stan in blue, the so-called Balagan formation. And together with Tim Smithson on the left here, Stan spent years on and off scouring these areas in the borders. And eventually, his persistence and unconventional techniques resulted in a major discovery. Now, although Stan and Tim had discovered a few spots that proved promising, I want to jump to this site first, as this is the one that really made the difference. This is Willie's Hole on the Whitadder River near Churnside. A couple of plant fossils, maybe nothing too startling about these plant remains, but indications of things to come. A few isolated bones started to pique the interest. Now, before I go any further, I should point out these fossils were not found in the river bank, but actually in the river bed itself. They could only be collected by feeling for the rocks underwater. So essentially, the search for fossils in this environment lacks any visual clues. So it was absolutely astonishing that Stan could home in on something as remarkable as this block. And I'm showing here a little bit more detail. This was the key first find, affectionately known as Ribbo. Stan knew that his efforts and gut feeling had paid off big time. And what you see on the top right are the prominent ribs, and on the bottom left, the clearly defined limb bones. Here is something that was used to living on land. And the ribs are important because that tends to indicate that this animal had pretty well developed lungs. Stan called me up and said that he had found something that he thought I might be interested in. Always one for an understatement. I was definitely intrigued. But when we did finally arrange to meet at his house in Selkirk, I was actually blown away by the extent of what I saw. This was clearly a major, major find. And this triggered a whole series of meetings with various colleagues, and the end result was the formation of the Tweed team under the leadership of Jenny Clack, yes, the one of Acanthostega, Ichthyostega and Poderpes fame. So Tweed, as Carol said at the outset, stands for Tetrapod World, Early Evolution and Diversification. And it comprises a major collaboration between 5 principal organisations, the Universities of Cambridge, Leicester and Southampton, together with the British Geological Survey and National Museum Scotland. And there was significant funding for the project coming from NERC, the Natural Environment Research Council, and also the Heritage Lottery Fund at the time. And these are some of the key members of the team. And the first thing to do was to try and get a sense of how these rocks related in time to the whole of Romer's Gap. What we needed was a section that represented the whole 15 million years from the end of the Devonian. The best way to do this was to drill a borehole through the whole sequence. This we did at Norham in Northumberland. We had various questions. How extensive were the rocks? What did they comprise? Could we correlate their ages across the whole region? And what could the sediments tell us about the depositional environment? Many of these questions were answered by the detailed study of the core, and you can see part of the core laid out in the shed on the right-hand side here. But it was also about getting more information on the fossils. Willie's Hole was one thing, let's get more. That was always Stan's motto. And Stan had shown that this was anything but a gap in the fossil record. Apart from Willie's Hole, Bournemouth was to prove to be another key area. And at Bournemouth, the beds in the coastal cliffs are almost vertical. Quite a challenge. But there is an extensive section running from the Devonian on the north side of the harbour, and I've used for the Devonian Acanthostega, down through a large part of the early Carboniferous to the south, and you've pretty well got the whole of Romer's Gap in there. Now, this is not the most conducive of fieldwork sites, with the ever-present threat of cliff failure, and you can see that sort of huge slump behind us on the upper picture. Nevertheless, the bones were calling. And you can see them in some parts coming out in the cliff, and Stig Walsh is pointing to a rhizodont fin spine there. We started to collect, these beds are sort of vertical, so we had to cut out blocks and sort of arrange a little bit at a time. So it was not an easy excavation. Now, if you look from the aerial view, it's a bit like our drill hole, the core sample, as I mentioned earlier, all laid out on its side. And we were able to partly correlate the two sections, the borehole with Bournemouth. And in there, we started to find finds including lungfish plates, tooth plates, as on the left, little feet up on the top pictures, and also little backbones, some really quite cool finds. And this unassuming piece of rock had a few scraps of interesting fish bone on the surface that looked like they might go deeper into the block. So we CT scanned it and were incredulous to find the remains of a tiny little tetrapod, a completely new species, inside. And this is the sort of scan being rotated of that particular block. So it's just a small slab of rock, and there is the block making you dizzy, I'm sure. So to stop getting dizzy, here are the main regions of the skeletal remains. We've colored them in different colors to show there's the skull at the top, that sort of conglomeration with the lower jaw in that sort of magenta color. And then at the bottom, you've got various ribs and clear limb bones. So we are starting to see a whole diversity of different forms in this region, in Romer's Gap. So is there potential for more? Yep, there is. You bet. Crumble Edge, an appropriate name, and consequently one we have failed to fully exploit. This is Jenny Clack at the bottom with her husband Rob. And we did find some significant bone fragments in the outcrop, but the cliff wall above was distinctly unsafe. So maybe one for another time. But wherever we started to look in those sort of blue areas, we started to see the various fragments of bone coming out. But back to Willie's Hole. Sure, the beds were not vertically aligned as at Bournemouth, and they dipped actually quite gently to about 30 degrees, but they were underwater and dipping deeper. And water levels are known to fluctuate wildly. But as always, Stan had a plan. We had a small window of opportunity each June when it was not active for fishing, and the water levels would be most likely to be on the lower side. So, armed with permits from Nature Scots and the permission of the Tweed Water Authority and SEPA, we dammed up one side of the river for 3 weeks. And with the dam in place, we were able to pump while on site and keep the riverbed completely exposed. So here we could systematically excavate in the dry. And it didn't disappoint. We soon started to find examples of plant remains, very rich branching patterns, stems, leaves, all sorts of things. And they were spread throughout. And we had a small office on site for sorting, labeling, and carefully wrapping all our finds. And these were taken back on a fairly regular basis during the 3 weeks back to Edinburgh. But we did collect a lot of this bed that Stan had first excavated 2 or 3 years earlier. And we LiDAR scanned the site so that we have a 3-dimensional record of the beds. And as a result, in the future, we can go back and pinpoint the beds exactly should it be deemed desirable to excavate further. However, this was the full extent of the excavation after the end of our field season. Quite a little quarry that we had created, and we had taken out vast blocks of carboniferous sediment. So at the end of the 3 weeks, the site was returned back to its original tranquility, albeit with maybe an added pool for the fish to lurk in. So what did we find at Willie's Hole? This, I hope you can see the sort of banded pattern. This is actually a really interesting and quite large scorpion. And we found other remains of scorpions, so it wasn't just the vertebrates we're after. Here, clear examples of terrestrial invertebrates. And the reconstruction is by Karen Carr at the bottom there of this new find. Millipedes, again, terrestrial invertebrates. So we are seeing this terrestrial environment. Various remains of large fishes, which were presumably in the freshwater ponds in the area, and even complete smaller fishes. So some really quite exciting vertebrate remains too. along with signs of various tetrapods. Limb bones of different types. This is another of those leg bones, a bit like a ribbo, a femur. Some of the fossils are very subtle, admittedly, but they have revealed a great deal of information about the terrestrial vertebrates living at the time in this area. And in this case, the enlarged eyes are really notable. There were at least 4 or 5 different tetrapod groups, quite significantly diverse groups living at Willie's Hole, all amphibians, admittedly, with a diversity of body types, as shown here in Karen Carr's reconstructions. And remember the ribs being evidence for land breeder. Also, up on the top right, you can see the humerus, the arm bone, the upper arm bone. And what I hope you can sort of see, you can see it in all 4 different views, is how it is twisted on itself along the axis. And this is what would be expected in an animal needing to support itself with its limbs out to the side in a sort of sprawling posture on land. This is clear evidence of a land-living animal. So, what was this area like 360 million years ago? We were south of the equator in a kind of a sort of subtropical archipelago. And this was the type of landscape, sort of the great forest typical of later on in the Carboniferous that yielded all the coal. They had not evolved at this time. So we've got sort of much sparser, lower vegetation with a few taller trees, meandering river channels, a few ponds, marshy ground, etc. And this is a nice little reconstruction of a scene in one of the pools. But this was a very dynamic environment, as told by evidence from the sediments, including the ones that we examined in the borehole. Periodically, there would be vast floods inundating the whole area, drying out to some extent, and then periods of actual complete drought. And in places, abundant charcoal tells us that there were times when extensive wildfires occurred. So much for the lack of oxygen that was at one stage posited as a reason for the Romer's gap, apparent gap. So where to from here? There are still so many unanswered questions. And this is a particularly intriguing fossil from Nova Scotia that is contemporaneous with the Balagan Formation. So that early part of the Carboniferous in Scotland and Northern England. These are clearly footprints, but they appear to have claw impressions. Now, claws only occur in amniotes. So these are reptiles, birds. I'm not saying these are birds, but reptiles. And so this begs the question, how do reptiles also evolve by this time? And was the transition to land by vertebrates actually even earlier than the beginning of the Carboniferous? Because for all this diversity to have occurred in this time, you have to sort of extend further and further back in time for the origins of these groups. Now, we don't know. We have not seen any body fossils that indicate the presence of true reptiles, but these footprints do look like they have claws on them. But maybe it's just an artifact of the way of the sediments and the animal walking through them. Finally, what was the driver behind the transition to land? Predators, that you're trying to escape from, fluctuating environment. I showed you those images of our restorations, drying out, flooding. That is quite an environment to be living in, and maybe it's better just to escape to somewhere that's a little bit more uniform. Or was it maybe the attraction of tasty arthropods on land? We know from the Rhynie chert that the invertebrates and the invertebrate communities started to inhabit the land much prior to the vertebrates. So it's a very complex question that I can't answer, but all the factors which I've just laid out were probably at play. And I think I shall just leave you with that thought. We've filled the gap, but now we're saying, is there a gap earlier in time that we need to start filling again? So I just want to thank Team Tweed and very much yourselves for listening, and I'm happy to answer any questions that I can. Thank you very much.